right, good morning, welcome back. Hopefully you made a really nice snowman. I made a giant one, the biggest one I've ever made in my life. It was like, I don't know, no, 10 or 12 feet tall. The base was like this big. It was awesome.
It's awesome.
And then my kids took a picture with it, making it look like they made it. So I'm like, hey, good for you. We had a good time with it. So today, everything's messed up, and we're going to try to correct things. So we should have notes out. We're going to talk about just a couple simple things because this hour now is shortened as well. We have to talk about a lab as well with that. A couple congratulations go out to, and I had to do a little finagling here because certain groups weren't the size they were supposed to be and other things like that. Esther Lab, there's actually a tiebreaker. There was many people tied, but unfortunately there was one group that had like 9 people having all the exact same answers, so that wouldn't have worked out very well. Said that you're supposed to keep it individual in small groups, so when 9 people all had the exact same 7 guesses, that can't be the tiebreaker when it's tied. So congratulations, it will be going on a trophy eventually to Miranda, Jenna, and Drew. They won the Esther Lab. They had the most correct, which was a total of 3 out of 8. Then Penny Wars, and I had to kind of make a decision on this because this was supposed to only be a 2-person group, and this was a 4-person, but 2 of these people were in the Esther Lab. So the winner of the Penny Wars with 363 drops was Erica and Emily. So congratulations to them. So pretty exciting. All right, today we're going to talk. Whoops. Okay, just make sure we get enough time on this. All right, reaction mechanisms. There's 2 things we're talking about today. We're going to do a couple demos as well, so it should be kind of fun. One you have seen before, but I've never heard anybody complain about seeing it again. So, a reaction mechanism. You've heard of people saying, like, the mechanism, it causes something to occur. A reaction mechanism is a really unique thing to kinetics, but to all of chemistry. It's a series of steps. And today, there's not actually a lot of notes. We're writing more drawings and drawing out some reactions. But a reaction might look really simple, like we do all through first year chem. Here, balance an equation. First year chem today, they're learning how to balance today. Here's an equation. But is that really all the chemistry that's happening? So, equation doesn't show all the details on what actually takes place. And the extra thing is, we may not know all the extra chemistry. We still have to take kind of a guess on it. So here's an example. And I would have written it right here, EX for an example. You got nitrogen dioxide and it reacts with carbon monoxide, and it just makes, and we're going to do one in a second as well, nitrogen monoxide and carbon dioxide. It's great. But that's actually not the chemistry. There are extra things going on. And your job is not going to be necessarily coming up with the steps. It's your job to interpret these steps. I'll say that again. You won't always have to come up with the steps. Your job is more about interpreting the steps that are given to you. Because there could be steps that we still don't know about, or other things that are happening. So here is an example of this. It actually happens in 2 steps. And I don't expect you to look at that overall and go, oh, well, naturally, those are the 2 steps. And we'll break this down more, but due to time, again, I'm having to kind of give you some bigger pieces of information and not going into it so much. So if you're looking at this and maybe you're not thinking this, but maybe something clicks and goes, well, that looks like Hess's law maybe. Like I could add up equations that make up one overall equation. I'd say, yeah, it kind of is like that. We can take multiple equations, add them all together, and what happens is certain things cancel out. Right, for just what's one compound that is not existent in my overall that you see? What's one? NO3, right? There's an NO3 here. It doesn't show up here. Anything else? Is there anything else in there? CO's right there. One of the NO2s is crossed out. So that's kind of a trick question, right? It's like it's already there. Well, there are ones, though, that do get canceled out from one side to the other. And then there's other ones that get canceled out, but kind of in a different fashion. What am I saying? I'm saying like this compound was kind of introduced, and then it was consumed. This one was created and then consumed in a different manner. But they both cancel out. These are 2 huge vocab words, and I know you probably heard of one of them, but probably not both. Catalyst. I'm hoping you've heard of that before. It's a species to speed up a reaction, and it's the yellow one, so you might want to draw an arrow actually. It's introduced. You have to bring a catalyst to the party. You have to bring a catalyst to the reaction. The other one's called an intermediate. It's not even a fancy sounding name. All it really means, it's descriptive in what it's saying though. It's an intermediate in between the equations. But the difference is this one's formed then consumed, okay? So then in parentheses I kind of wrote, I think the big thing you're looking for. A catalyst, it's introduced. An intermediate, it's created. We have that. We are going to talk about one of my favorite reactions. You've seen it during chemistry. But it's the, it's a decomposition of hydrogen peroxide. It's the only other example we have on here, and then we'll get into our other topic. But it's really not that exciting if you just watch the decomposition of hydrogen peroxide. I have to wear gloves. This is 30%. Hydrogen peroxide, what you have at your house is 3%. If this gets on my skin, it will turn it extremely white. I've never had this happen. I had a colleague have it happen to them once. Why isn't it coming out? And they could barely speak because it hurt so much. I'm afraid of it coming all out at once. It's all in the grooves. Come on. Okay. I don't know. Doesn't help much, actually. There you go. A little bit more. Actually, I need a lot more. Oh, good. All right, so if I just have it sit here, or I'm going to put it right here right now, it's decomposing. Why is it in a brown bottle? Through the murmurs and the whispers. Sunlight, UV, can break it down. So it can decompose. It has a shelf life. It doesn't have a tag on here right now, but it's a shelf life pour. If I kept this in the, that's why I'm also using it up in the storage room for the next year, it wouldn't really be that effective anymore. So it does break down. It does decompose into water and oxygen. So really not much there. And much to react later. But we could add a catalyst and we could speed this thing up. Thanks. So we could go from that compound to water and oxygen just faster. I'm still going to do the exact same reaction from start to finish, but there's a lot of unseen things that maybe could have happened. So what I'm going to do is I'm going to add a catalyst. Oops. So what I'd like you to do right now is I'd like you to label, either put like a C or an I for intermediate or catalyst. What is my intermediate and what is my catalyst? Now they don't both have to be present. Say that again. You do not need a catalyst and an intermediate. If I ever ask you to identify if anything's present, you have to be aware that you're just looking for what is canceled out and how did it come to be in the reaction and how does it cancel out. So it matters the order. If I flip equation 1, equation 2, then that changes what was introduced and what was created. So what is my catalyst? Iodine. I have potassium iodine right here. Well, that is my catalyst. That's going to speed this thing up a lot. But to make it a little more fun, I want to trap the oxygen. So I'm going to put some soap in there. That's the only reason why that's in there. And let me shake that up. Oops, can't do that anymore. Just put that in the hydrogen peroxide. All right, we'll just hope it mixes. Yay! Elephant toothpaste. Happy comes to me. Usually it comes out really solid. I don't know why it's like kind of breaking up, but I think it's starting to break down a little bit. So that happened really fast. It's the exact same reaction. I just want you to kind of be aware of that. Like it's the exact same reaction. I just sped it up. The thing is just chock full of oxygen right now. All right, so hopefully you cross out iodine. You cross out IO minus for your intermediate, okay? So that is a great example of what a catalyst can do for a reaction. Okay, I'm just going to leave that there for right now. All right, another thing that I want to talk about is this piece of paper. So my dad, very exciting, I know. Yeah, Kevin. It's awesome the microphone was off that entire time. Well, that's going to be the catalyzed pathway. That's why a reaction goes faster, because the pathway is shorter. And I hope that makes some sense. Like, oh yeah, like if I was on a bike, this would not take as much time before.
So does that mean that like catalyst things are always excellent?
No, not necessarily. Like you could have something up higher here. It's just the pathway would lower the activation energy. That's all. So the peak would be lower. Okay. So all I have is one last thing. So hopefully you have that drawn. Okay. So we have an equation for this. It's in your packet and on Kinetics 2. You should have been working on already. So it's not something about memorizing, it's about applying. Please know the difference. One thing you will notice, and I want to point this out, is that you have K2 over K1. What you're doing is you're comparing two different reactions of the same type of reaction, but at different conditions. So right away, you can notice that we have 1s and 2s on temperature and 1s and 2s on Ks. Oh, so wait, when I change the temperature, it changes the rate constant. Because changing temperatures cause reactions to, or molecules and compounds to move faster or slower. So a reaction can happen faster or slower. So if I lower the temperature, the K probably reduces. If I raise the temperature, the K increases. So you have to have two different conditions. Because of that, we can figure out some different things through this. Couple things to notice though. If for whatever reason that you are provided, when you are provided this equation and this has K1, you'll notice this will be T2. If these flip, these just flip. So don't allow that to be a huge confusion. It's still the same thing. Sometimes what people actually do is use that to their advantage if they're wanting a certain variable wherever they want it. Like I want that on the bottom or I want that on top, I can just flip those items. This is activation energy, and then R is the R that we are given always on our yellow sheets, our equation sheets. And why I know that one I have to use is because that one has energy in it, that has joules in it. Okay, so that's what that's about. So that is the last of your notebook notes. Are you right back?
Sorry, he was so happy. You got it on
I've been playing like a week and a half.
I The constant and like.
Okay, so you have, and it's kind of gotten a little screwed up. Why did I do that? With the snow and all that, but we have a lab dealing with acid rain and marble statues. And I'm not going to give you a lot of insight, or there's no procedure whatsoever. It's all about you figuring it out yourself and figuring out what you want to do. Now, we were going to do this in an easier way, and I was going to give you all this equipment in the middle of the table. So tomorrow, that's what you're going to see in the room. It's going to be all this different stuff that you can choose from. A lot of it's not useful. Some of it is. And that's going to be kind of your choice to figure that out. Okay? But I want to just show you something to kind of get you thinking about this. First, I want you to think about kinetics 1. And what that means is that we did different experiments to isolate what the rate was, how fast things were reacting. So if you look, I've given you a bunch of information that's on this sheet. It talks about the challenge. So here we go. It says, challenge. Your task is to investigate how the speed of a chemical reaction between solid calcium carbonate, which is a lot of what is in a marble statue, and a solution of hydrochloric acid is affected by changing variable relating to the two reactants. You will implement the investigation by first constructing and then testing a hypothesis. So I want to just show you something. I'm not measuring anything out like this, but here are my two reactants. Marble chips, which I will show you right now. Of course it is. And of course you can't see anything, so let's turn on the light. What?
Is the packet due today still?
Guess I can give you a day. Not like it's fine. I don't know why I need to extend it though. You've had a whole day off,
I
right?
didn't know, I was just curious.
Then why are you asking?
Because other people.
Well, then make them ask. Don't be the voice for them.
I'm the voice.
All right, so here's the marble chips. What I'm going to do, we would weigh them, but this is what I want to do instead. And you would record all that. And there's different size chips and all that good stuff. I am actually going to now, here, let me get goggles on. I'm going to use 6 molar HCl. But it doesn't have to be 6 molar, so that's concentration. And I would measure how much, but I'm just going to, oops. I'm going to put a certain amount in. Okay? And what I want you to see, without me giving, like saying things, but I just want you to understand that there's things we can measure. Can you see that? Kind of. It's hard to tell. All right. I'm going to put this balloon just so it's weighed on here. And now I'm going to hit 0. So 0 right now, okay? What I'm going to do is I'm going to put in the marble chips. And show you a couple things. Just start brainstorming. What you need to do is probably really focus, because I'm not going to help at all during the whole lab. You need to start figuring out how can you test concentrations that affect rates without changing other things. What can you do? How can you test these things? And there's all sorts of different ways. So I'm trying to give away multiple ways that you can test this. So if I throw the calcium carbonate in there, I'm going to put a balloon over this once just to show you. And you have the chemical equation. Maybe this shows you nothing, maybe it shows you something. But if you look, you can also see, I'm sorry, it's kind of a glare. How do I don't know if you can tell. Now because I'm trapping, it's not going as much. You should be seeing that the mass is dropping. The problem is it's only dropping a little bit because I'm actually still trapping the gas. If I open that up completely, the mass would be going down a lot more, I would think, right? So how can I test? I have chips, okay? I have acid. How am I going to start being able to make a table like Kinetics 1? A table where I can figure out the different rates. I can measure rates then. I can actually calculate them, and I can figure out the order of this reaction. What could I all test? So I'm going to have all sorts of different stuff in the middle of the table tomorrow on Thursday, and you're going to be able to start looking at it. It's going to be a bunch of different probes. There's going to be a temperature probe, a pressure probe, there's like a pH probe, a bunch of different probes. Like, what could you use? What don't you need? You have access to balances. You have access to diluting and making the acid more concentrated. You have access to the chips in any way you'd like. How could I start testing to figure out rate of reaction of my two reactants? And there's only two on your sheet. So there's calcium carbonate and there's HCl. Okay? This is the only sheet you're going to be getting besides a post lab. So it will be your job to start figuring this out. Now, this is the tricky part. Tomorrow you're going to be in class with people that may not be in class with you on Friday. So if you can kind of foresee that, you might be able to kind of brainstorm with them earlier if they're in your Thursday class right away. But regardless, when we all come together on Friday, whoever you're going to be in with your group, you're going to have to start figuring out, okay, this is what I think we should try to do with this reactant. This is what I think we should try to do with that reactant. And we're going to have to start to test it. This is harder, much harder than just giving procedures.
Should we just come in later if the people that are taking St. Norbert's test? Yeah, just go.
Well, you're going to be done with the test after AP, right?
Don't you have
Isn't it?
AP classes 1
It's
through
supposed to
4?
go mod 1.
Oh, if you can make it to 4, but you might have classes on 4. If you're open on 4, you're definitely welcome to come in. But after that, just the class is done. So tomorrow's about brainstorming and looking at it, start formulating. We're going to start creating our sheets. Tomorrow also you'll be getting Kinetics 3. Unfortunately, just with the snow day, I had to kind of alter what's on it, and I just don't have enough time to have gotten it done. It's very short. It's one-sided, and all it has to do with... Do we have timer?
I don't think how long our classes go.
It goes until 55. That clock's fast, isn't it?
No, I think changed it. That's 52.
Okay, well, we have 3 minutes. I don't think it takes that long to get back up. Alright, so anyway, I don't remember where I was going with that, so I guess we're done.